If you try to push a body, then the body shouts and says, I don't want to move, I want to remain at rest. And if you try to push your dead car, then the dead car says, I don't want to move, I want to remain at rest. And if you try to stop a moving car, then the moving car says, don't try to stop me, don't waste your energy, I don't want to stop. So we need efforts to move a body at rest, and also we need efforts to stop a moving body. Why a body at rest cannot move itself, and why a moving body cannot stop itself. This can be well understood by concept of inertia. Now let us define inertia. Tendency of a body to oppose in its state of rest or oppose in a state of uniform motion in a same straight line, unless it is acted upon by an external force, is called as inertia. The law of inertia was first proposed by Galileo Galilei, and after that it was upgraded by Isaac Newton as Newton's first law of motion. Newton's first law says, if you wish to move a body, then you must apply some force on it. That is, a body can move only if unbalanced forces acting on it. And if you wish to stop a moving body, then you must apply a balanced force on the body in opposite direction of its motion. Newton's first law of motion helps us to define the term inertia. According to this law, inertia is fundamental property of every physical object by which the object opposes any change in its state of rest or state of uniform motion. Inertia helps us to understand behavior of objects at rest and at motion. Inertia of an object depends upon its mass. Greater the mass, greater the inertia. Since mass of the truck is more than the mass of car, hence inertia of truck is more than car. Inertia, the word refers to linear motion, and moment of inertia refers to rotational motion. Now, let us understand the concept of moment of inertia. For a body to move in a straight line, we need to apply force. And if we wish to rotate a body about an axis, then we need to apply a twisting force called as torque. Let us try to understand moment of inertia by taking an example of opening the door. We need efforts to open the door. Opening of door is as good as rotational motion. Efforts needed to open the door depends upon two factors. First one, mass of the door. Second one, perpendicular distance OP from the point of application of effort and axis of rotation. Thus, the rotation of body not only depends upon mass of the body, but also depends upon the distribution of mass around the axis of rotation. Now, consider a body of any shape rotating about a given axis. So, this is a rigid body rotating with angular velocity omega, and we assume that the body consists of n particles, and mass of the first particle m1, mass of the second particle m2, mass of the third particle m3, and so on. Mass of the n particle is mn. Now let r1 be the perpendicular distance of mass m1 and r2 be the perpendicular distance of mass m2 and r3 be the perpendicular distance of mass m3 and mn, for mass mn the distance rn is a perpendicular distance. So we got here all perpendicular distances of respective masses. When the rigid body is performing rotational motion, the particles present on the rigid body, they perform uniform circular motion. So this circle stand for uniform circular motion. I repeat once again, when the rigid body performing rotational motion, then the particles present on the body perform uniform circular motion. And particle with mass m1 will have linear velocity v1 and the particle m2 will have linear velocity v2 and the third particle linear velocity v3 and so on. The nth particle will have the linear velocity vn. Summary: first particle m1 will have linear velocity v1, second particle will have the linear velocity v2 and the third particle will have the linear velocity v3 and so on. The nth particle will have the linear velocity vn. And angular velocity of each particle is remaining the same. That means the angular velocity of m1 is omega, angular velocity of m2 is as well as omega, and angular velocity of the third particle is also omega, and so on. The angular velocity of the particle mn will also remain omega. So the angular velocity not changing, only the linear velocity is changing. Now for the first particle, we have the linear velocity v1 which is equals to r1 multiplied by omega. For the second particle v2 equals to r2 into omega. For the third particle v3 equals to r3 into omega, and for the nth particle vn equals to rn into omega. As every particle is performing uniform circular motion, every particle has translational kinetic energy. For m1, translational kinetic energy, let us call it as a ke1 equals to half m v1 square, that is equals to half m1, and v1 is nothing but r1 into omega whole square, so that is equals to half m1 r1 square omega square. Similarly, kinetic energy of the second, translational kinetic energy of the second particle, half m2 v2 square, that is equals to half m2 r2 square into omega square. Similarly, for the third particle, translational kinetic energy half m3 r3 square and omega square, and so on. For the nth particle, the kinetic energy, translational kinetic energy half mn rn square omega square. Now total rotational kinetic energy of the given object is addition of all kinetic energies, that is ke1 plus ke2 plus ke3 and so on plus ken. So addition of all kinetic energies, we get half and omega square is taken common. In the bracket we get m1 r1 square plus m2 r2 square and so on mn rn square. Now the quantity m1 r1 square plus m2 r2 square plus and so on plus mn rn square, this quantity nothing but called moment of inertia. Moment of inertia of the given object. Moment of inertia of the given object can be denoted by I. Therefore, I equals to summation 1 to n mi ri square. Therefore, the rotational kinetic energy of the given object is equals to half I omega square. So this is the rotational kinetic energy of the given object about given axis. Every rotating body will have the kinetic energy, and the kinetic energy of the rotating body is given by the formula half I omega square, where I is nothing but called as a moment of inertia. Therefore, rotational kinetic energy of the given object depends upon moment of inertia. Now, rotational kinetic energy given by half I omega square and translational kinetic energy given by half mv square. Now, this rotational kinetic energy is analogous to translational kinetic energy. Now, what is the similarity? The I is nothing but analogous to m, and omega is analogous to velocity, linear velocity. Thus, moment of inertia is analogous to mass in rotational motion. Second point, moment of inertia gives how an object opposes rotational motion. The third one, moment of inertia is rotational equivalent of mass. From above discussion, following points are clear. That is, moment of inertia depends upon individual masses present in the given object or system. Moment of inertia depends upon the distribution of masses about the given axis of rotation. Moment of inertia changes if you change the axis of rotation.